Good day, students. Welcome to AP Calculus AP Exam Review. We're going to be looking at problem number 2 on the 2012 unreleased questions. This problem focuses mainly on area between curves and volumes of solids of revolution. All right, so let's take a look at question 2. It says, let R be the region in the first quadrant bounded by the x-axis and the graph y equals ln x and y equals 5 minus x, shown in the figure above. Part A, we have to find the area of R. All right, so there are two ways we're going to find the area and we'll get the same answer. We're going to use a vertical orientation and a horizontal orientation here. I'm going to classify them as methods 1 and 2. So for part A, method 1, we're going to use the method of vertical rectangles. Okay, so what do I mean by vertical rectangles? Well, what we're going to do is we're going to divide this area into infinitely narrow vertical rectangles. Okay, they're going to look like this, and their widths are going to be dx. Okay, so basically you have this rectangle. You're going to break this entire region into really tiny slices of vertical rectangles, and then we're going to find the infinite sum of the infinitely many rectangles. All right. Okay, so the formula for finding the area of a region bounded by two curves is given by, so area equals the integral from a to b, the boundaries of the functions of the function on the top minus the function on the bottom. Let's call that g, okay? Function on the top minus g on the bottom. And that should basically help us calculate the area. So let's say g of x on the bottom, and then f of x on the top. We gotta include our variables here. Dx. This is for a vertical orientation of our rectangles. Okay, all these values are all x's. So x equals a, also x equals b. Our function will be in terms of x and dx. Now, if you take a look at this situation we have here, we have two functions on top and one function on the bottom. Let's deal with the bottom function first. In this region, we have only one bottom function, g bottom of x is basically equal to 0. Okay? Now we have two functions here for our top function. Here we're gonna, let's call this f1 top. So this is the logarithmic function, ln of x. And then we have another top function right here. So this is f2 top. Okay, f2 top, which is the linear function 5 minus x. Now what does this mean? Well, it means that we must divide our integral into two expressions because we have two distinct top functions. So for the first one, we're going to integrate from 1 to the x-coordinate of this intersection, and then from the x-coordinate of the intersection to 5 will be the limits of integration for our second area. Okay, so basically we can look at it as two regions, regions 1 and regions 2, and we have to do them independently. Okay, all right, so in order to set up our integrals, to know the limits of integration, we have to use our calculator to determine the coordinates of this point of intersection. All right, I'm going to demonstrate how to do that using two calculators, the TI-89 and the 83. Whatever method I use for the 83 is also applicable to the 84s too, okay? So for the 89, let's start with that. We're graphing two functions. The first one is the natural logarithm of x. Enter, and then the second one is a linear function 5 minus x. Enter. Let's go ahead and graph it. There goes your logarithmic function. And then there goes your linear function. We're going to be calculating the intersection, so we're going to go to the math menu of the graphing window, so F5, and then option menu number 5 will help us calculate the intersection. First curve should have the cursor on it, blinking, press enter. It gets selected. Second curve with the blinker, press enter. it gets selected and asks for the lower bound. Any point to the let's do that again. Let's see. F5 intersection, first curve, second curve. Any point to the left of the point of intersection is your lower bound, so let's pick that point. And it asks for your upper bound. Any points to the right of that intersection will be your upper bound. Enter, and there goes your point of intersection. Okay? In your RTI 83 or 84, let's do the same thing. For y, just enter lateral logarithm of x. And then for the linear function, 5 minus x. All right, now let's calculate the intersection. To do that, we use second function trace. Calculate is option number 5. So we have the functions graphed first. Now it says which is the first curve. Have the cursor selected, enter. Second curve, enter. It says guess. Since there are only two functions and one point of intersection, it's pretty easy and straightforward. Bam, there goes your intersection. 3.69344 and 1.30655. All right, so let's go ahead and write down the point of intersection. So it's going to be, oops. All right, so let's write down the point of intersection. So we have 3.69344 and 1.30656. Okay? All right. Now, for our integral right here, we're going to be focusing just on the x-coordinate right here, okay? So now let's apply this to this setup to this formula right here. So for region 1, we're going to set up region 1 and then 2, okay? So the entire area is going to be the integral from, for region 1, we're going to go from 1 to 3.69344 of the function on the top. Function on the top is the natural logarithmic function, ln x, minus the function on the bottom is 0. Okay, so that's the expression for the area for region 1, dx plus. Now we have to add the area of the second region. Okay, let's go ahead and set that up. That's going to be the integral from where we stopped before, 3.69344, all the way to, this is 1, 2, 3, 4, 5, that's 5 right there, all the way to 5 of the function on the top now changes, that's why we have two integral expressions, to 5 minus x, let me use a different color, now changes to 5 minus x, 5 minus x minus the function on the bottom is still 0, so minus 0. All right. Okay, and now if you plug in these two expressions into your calculator, I went over how to do this. Use your calculator to do integrals in part 1, so you can refer to that. I'm just going to show you the answer. The answer is basically 2.986. Okay, now let's try another method. How about we do horizontal orientation of our rectangles, and then we compare the two methods to see which is the best for this problem. So we're still doing the same. Section A, method 2. Method 2, we're going to use horizontal orientation, okay, horizontal rectangles. Now for horizontal rectangles, what will our variables be? Well, let's set up our rectangles. So horizontal rectangles, we're going to slice this region into infinitely many horizontal rectangles. Now, what's the width of our horizontal rectangle? How thick is it going to be? It's going to be dy. Okay, so everything in this function will be in terms of y, okay, for our entire setup. Now, if you look at the orientation of these two functions, let's assume that you are standing on the y-axis like this, and your head facing up like that. Which of these will be the top and which will be the bottom? we can clearly see that this linear function right here will be the top. So this would be f of, was in terms of y now, this would be the top function. And then this piece right here, this will be the bottom function. This would be g of y. This would be the bottom. Okay? All right, so what are the value of these functions? Let's go ahead and figure them out real quick. We know that for the linear function, y is equal to 5 minus x. So if you solve this, you're going to have, let's see, x is equal to 5 minus y. And then for the other one, we have y is equal to e, no, it's ln, sorry. Y is equal to ln, natural logarithm of x. And then if you want to get x isolated, you exponentiate both sides. E to the y is equal to e to the ln x. Ln x, so here we're going to have x is equal to e to the y. All right? So our functions, the bottom function is going to be the inverse of the logarithmic function, which is e to the y. And then our top function will be the inverse of the 5 minus x function, which is 5 minus y. So this would be 5 minus y. So there you have it. Okay? Now, you notice how nice this setup is? We have exactly one function on the bottom and one function on the top. That means that we do not have to jump or use multiple integral expressions to represent the area. Okay? So let me set up the integral for you real quick, but we need the y-coordinate of this point right here. So this point again is 3.69344, comma 1.30656. All right, so our integral using this formula is going to be the integral from, let's just set it up again. So integral from a to b of f of y on the top, okay, in the y direction, or technically, let's call it right and left, okay? So f of y on the right, because it's further, minus g of y, to the left, okay? Left, right, right, left is the same orientation as top, bottom, okay? Because the values of the variables are increasing in that direction, so are decreasing in that direction. So that's dx, that's the expression for your area. So this is very straightforward. This is going to be the integral. Notice that this variable here is supposed to be a dy, because we already talked about that. The width of our rectangle is dy. So just make a real quick check. Everything has to be y, 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 y. Okay? So limits of integration, 0 to the y-coordinate of the intersection, which is 1.30656. So from 0 to 1.30656. Please do not use the x coordinate. That's a big mistake many might make. You're going with the y's. That's all that counts here, okay? Times f of y. Our f of y function is 5 minus y, minus our g of y function, the function on the bottom, or to the left, is e to the y, so minus e to the y. Okay? Now if you plug all that into your calculator, you're going to get the same answer, 2.986. All right, let's take a look at the B part. It says find the region. Region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. Write, but do not evaluate an expression involving one or more integrals that gives the volume of the solid. So let me give you a sketch of the situation, and then we'll see if we can determine what the volume setup is. All right, so let's say this is the function. This is part B. Now let's see that let's rotate the y-axis a little bit, okay? Rotate the y-axis. So let's see the y-axis was rotated downwards. Now, what this problem is telling us is that the cross-section of this region is the base of a square, but the cross-section has to be perpendicular to the x-axis. Okay, so this is one cross-section right here. something like that. That's one cross section. Let's use a different color. How about we make it red? Okay, so this is one cross section, and then we also have another cross section here. Okay, try to make them parallel to that other line. Now you might wonder, why am I making two cross sections? Well, because we have two different functions that define the length of this cross section. Okay, so for the first region, let's divvy up our regions because we have two functions. For our first region, what we have is a cross section with this length right here. The function that we're looking at for this region, let's put it in red. This function is the natural logarithmic function, ln x. Okay, and then for this function right here, uh, um, let's call this f2 of x. f2 of x is 5 minus x. Okay, so these are the two different functions that we can use to compute the dimensions of our square. All right, so here we're going to have a square with this base. The length of this is basically 0 minus this function, and the length of this is 0 minus that function right there. Okay, so let's go ahead and draw the squares. Okay, so there goes the squares. Now, what we have is an infinite number of squares like this, oriented along this curve. All right, so we have a lot of them. This is just a snapshot of two of them. So what we're going to do now is set up the formula for the volume. Now, the only thing we care about to find the volume is the area of these two faces. So the question is, what is this area right here? A of x. What is that area? And then what is this area right here? Wrong color. What is this area right there? Because that's what we need. Okay. So these are squares. We know the formula for area of squares. The area of a square is equal to s squared, where s is a side length. So what is the length of this segment right here? This segment goes from 0 to ln x. So s is basically going to be ln x minus 0. So s squared is ln x minus 0 squared, which is just ln x squared. That's the area of this face. And then this one, the same story, but a different function. The length of this segment is 5 minus x minus 0. Oh, wait, let's write out the area formula first. The area of a rectangle is s squared. So this is s, so it's s squared. So it's going to be 5 minus x minus 0 squared, which is basically 5 minus x squared. Okay, so why are we looking for a to the x? Because of the formula volume. The volume for the formula. Okay, so the formula for the volume is the integral from a to b of the area of the cross-sectional face, dx. We have two unique functions here that determine the dimensions of our square, so we have to divvy up our area into two expressions. The first one is going to be the integral from 1 all the way to the x-coordinate of the point of intersection, which is 3.69344, of the area of the face, which is the red function. In this case is the natural logarithm of x squared, because ln x minus 0 is the length of the side, and you just square it to get the area, dx, plus the integral, continuing from where we stopped, 3.69344 all the way to 5. Here, the area of the face of the square, sorry, is 5 minus x squared dx. And that's basically the expression for the volume of your solid with the given cross-sectional area. Now let's take a look at part um, part C. It says that a horizontal line y equals k divides R into two regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. Okay, so let's take a look at let's sketch take a snapshot of the graph again. So this is portion C. So we have a horizontal line somewhere in this between this x-axis and this vertex right there. That horizontal line divides this region into two equal areas. Okay, so these two areas are equal. So the question is to set up an integral involving k in such a way that we have that integral expression represents half the area. All right, so how are we going to orient our rectangles? We can clearly see that this is a dy situation, okay? We're going to be orienting our rectangles horizontally, okay? That'll make perfect sense since the limits is along the y-axis. So this is going to be dy. Now, how do we set up the expression for our integral? Well, we're simply going to have the expression for the area. Remember, we talked about this before. The integral of the function from the top minus the function on the bottom, right? In this case, is dy. If you're standing on the y-axis, like indicated earlier, this is the top and that's the bottom. We already set it up before, so let's just copy that down. So it's going to be the integral from 0 to k of the function on the top is 5 minus y. Remember, this function right here is 5 minus y. And then minus the function on the bottom is e to the y. Okay. dy. It said this integral is equal to 1/2 of the area of the entire region, which we found out before to be 2.986. Okay, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel and post a comment to let us know what you think about this clip. More review tutorials can be found on mathgridserve.com. Thanks again for watching and have a wonderful day.